Great pleasure to introduce Alessio Sammartano. Alessio was a PhD student at Purdue and then a postdoc at Notre Dame, and now he has a position, also a postdoc at SLMAF when he was still MSRI, and now is a professor, an associate professor, I think, at the Polytechnic of Milano, and is going to talk to us about Cartwright-Strunfeld's ideals and smooth Hilbert scheme. And this is joint work with Ritwik Ramkar. Thank you.
Thank you, Claudia. Thank you for the invitation. I'm very happy to be speaking here. Yes, so this is a collaboration with Ritwik that we're almost finishing, and we hope we can put on the archive soon. So I'll be talking about Cartwright-Strunfeld's ideals, which are a particular kind of multi-graded ideals. So I'll first start setting up the notation for a multi-graded environment. So choose some integers, a1, a2, to an, representing n sets of variables. So we have a polynomial ring S over some field in n sets of variables, so I'll denote them by xij. So each set has ai variables, so j goes from 1 to I goes from 1 to n. And we should think of this as, for instance, the coordinate, the multi-homogeneous coordinate ring of product of projective spaces, which I'll just denote for simplicity by P. Okay, so P is the product of P of the appropriate projective spaces with that many variables. So as I said, this is a multi-graded polynomial ring. So this is a direct sum decomposition into multi-graded components that are graded by the semigroup n to the n, and so degrees will be vectors. So use the underline d for a degree in this semigroup, and brackets for graded components. So this is the multi-graded by it gives a grading like this. So xij as for degree, the ith vector of the canonical of the standard basis of n to the n. So this is in some sense a standard multi-graded polynomial ring because every variable has total degree 1. So first I'll go through some basic very familiar concepts and facts that you have in the standard graded setting, but you can also extend in a multi-graded setting such as this. So if we have an ideal that is homogeneous, so everything degree related will be about the multi-grading. So here homogeneous refers to the multi-grading. So then we have the most important invariant of this talk would be the Hilbert function. So the Hilbert function, so think, for instance, an ideal as the ideal, for example, of a variety of the product of projective spaces. Then we attach to this algebraic or geometric object a numerical function that is a function that I'll denote by hf sub I from the semigroup n to the n to the negative integers. And we could do either the ideal or the quotients. Maybe the quotient is a little bit more natural. So this that sends the degree d to the dimension of the corresponding graded component as a vector space over K. Okay. So this, we'll talk about Hilbert functions a lot. So this is a multigraded Hilbert function. What else we can do in general? We have a general linear group, more or less. So I'll denote by GL the product of the general linear groups on each set of variables. So this product acts on the polynomial ring, or on the product of projective spaces by changes of coordinates. So changes of coordinates that are that respect each factor. And inside GL, we have a Borel subgroup that I'll denote by B. So this is just the product of the corresponding Borel subgroups in each in each factor. And so here, let's see, B of A is the subgroup of upper triangular invertible matrices in each group. GL. Okay, so I'm doing this because I want to talk about initial ideals and generic initial ideals. So so now we'll talk about initial ideals in this multigraded environment. If we set now, I'll be scrolling, obviously. So if I'm going too fast, if there's any question, just let me know at any time and I'll stop. So if we fix a monomial order on S, then we can talk about generic initial ideal as follows. So we have the following fact / definition. That there exists an open set in the open subset of the group GL, where the initial ideal is constant. So where I will take my ideal I, change coordinate by taking a change of coordinate in this open set, and then take initial ideal of this ideal where I have changed coordinates, and this will be the same. Okay, so this will be constant. This monomial ideal that I get with taking initial of all these ideals where I've changed coordinates will be the same on a whole open set, and therefore it makes sense to give it a definition and call it generic initial ideal. So the gin of this ideal of an ideal I is defined to be one of these initial ideal where we change coordinates generically. So this is called generic initial ideal of I. And some basic facts about this construction. So we start from a monomial ideal, from a homogeneous ideal in the multigraded polynomial ring, and then we do this change of coordinates, initial ideals, and so on. None of these operations affect the Hilbert function. So we have some basic facts. One is all of these ideals have the same Hilbert function. So the one that I take by changing coordinates, or if I take a initial ideal or the generic initial ideal, then all of them have the same Hilbert function. And okay, this is pretty easy. And then the second one is that this particular one that I constructed, the generic initial ideal, is Borel fixed. So it is fixed by the action of this Borel subgroup B, which means that not only it is a monomial ideal, of course it's a monomial ideal being the initial ideal of something, but it is again a Borel fixed ideal, which is a very special type of monomial ideal with good combinatorial property. So this is already saying in some sense that if I start from any ideal with any Hilbert function, I can cook up another one that has the same Hilbert function. It is also Borel fixed. All right, so this is about all of the preliminaries that I need. So now I can go on and introduce the main definition of the talk, the notion of Cartwright-Stumpfels ideals. So this again will be a theorem/definition. And this is part of a theory that has been developed in the past few years mostly by Conca, De Negri, and Gorla, for instance, in a paper in 2018, but also in some other papers, and also by some other authors. But here you will find the following definition. So first of all, the following theorem, with notation as above. The following conditions are equivalent. One, that the homogeneous ideal I as a generic initial ideal that is a radical ideal. So radical will be a crucial property throughout the talk today. And then some more. So this is in particular saying that there exists a Borel fixed ideal that is radical and has the same Hilbert function. So we could also take that other condition, which turns out to be equivalent. So there exists another ideal J that is radical, Borel fixed, and with the same Hilbert function. A priori, it doesn't have to be the generic initial ideal, but in fact, it turns out that it has to. And then there is some in fact, stronger conditions, I mean, apparently stronger. One is that every ideal, Borel fixed or not, let's say I prime in S, that has the same Hilbert function must be radical. And then the strongest of them all, that for this Hilbert function, there exists a unique Borel fixed ideal. So denote them by J, if it's Borel fixed, with the same Hilbert function as I. And this unique Borel fixed ideal has the property that it is radical. Okay, so some of this, so these four conditions are equivalent. Some of the implications among them are obvious and then trivial. Some are surprising. Okay, so for instance, the fact that if I have a Borel fixed ideal that is radical, then there's only one Borel fixed ideal. So 2 implies 4 is perhaps the most surprising of these 4 equivalent conditions. And 3 shows how these conditions are in fact very rigid, very strong. So we're asking that every possible ideal with the same Hilbert function is radical. In any case, this is the conditions that bear the name Cartwright-Stumpfels. So in this case, if I is a homogeneous ideal that satisfies this equivalent condition, then we give it the name characterized Stumpfels. So I'll try to say characterized Stumpfels each time, but maybe I'll just write CS for short. Characterized Stumpfels because the three authors were inspired in part by work of Cartwright and Stumpfels, which I'll mention in a second. So I'll spend a few minutes in trying to convince you that this notion is interesting and that this class of characterized Stumpfels ideal is, in fact, a good class with good properties, and in fact, they appear in many different contexts. Let me pause for a second, maybe, and see if there's any questions. Okay, so if not, I'll go ahead and see what are the basic properties. Why are these characterized Stumpfels ideals special? So let's see just a few of them. So if I have an ideal in the polynomial ring that is CS, and it's also useful to keep track of the multi-grading. So maybe I'll write explicitly this is an n to the n graded ideal and characterized Stumpfels. One consequence is that it has in some sense, a good resolution, good free resolution. So specifically that Castelnuovo-Mumford regularity is bounded by n, which is the dimension of the semigroup where the degrees take place. And in fact, for instance, if the ideal is generated in degree n, which is not uncommon, then it has a linear resolution. So the nicest possible resolution. This already shows that this notion is a genuine multi-graded notion. If this was a single grading, if n was equal to 1, then we wouldn't be getting any interesting ideals. These would all be ideals of regularity 1, namely ideals of linear forms. So, but in the multi-graded setting, there are in fact many interesting ideals, as we will see. Okay, so in terms of Grobner basis, as you may imagine, the definition itself involves Grobner basis. So this, in fact, has important consequences for Grobner basis. So one consequence that is obvious, but still interesting and worth noticing is that all the every possible initial ideal of I is square free. So tau here is an arbitrary monomial order. We know that square-free monomial ideals are the ones that are rich with interesting combinatorics. So this will be the case here as well. And special property in terms of universal Grobner basis is that this ideal has a universal Grobner basis that is generated in degrees at most 111. In particular, total degree n. So universal Grobner basis is a Grobner basis that is universal in the sense that it is a Grobner basis for every possible term order. Such things exist, but in general, they're hard to control. So in this case, there's very good control on the degrees of the universal Grobner basis. And once again, if the ideal is generated in degree n, that means that the minimal generating set is a universal Grobner basis, which is an extremely strong property. There's also other properties I'm not going to write. This class is stable under a lot of reasonable operations, such as hyperplane sections and columns and so on. And yeah, in general, we see that this either these properties or this equivalent condition will tell us that for this class of ideals, there is the connection with monomial ideals is very strong. Okay, so there is a distinguished way of attaching monomial ideals to a characterized Sturmfeld ideal, and this would preserve a lot of the algebraic properties. So we will see this in the examples as well. That's a class of ideals that can be studied combinatorially in many contexts. The second main reason why these ideals this notion is good is that this is a good unifying notions for variety of examples, some from fairly different contexts that now can be treated in the same way. So I'll show you now that there's a lot of interesting classes of characterized Sturmfeld ideals. So the first natural place where to look for multi-graded ideals is determinantal ideals. And here we have lots of examples. So we have ideal of maximal minors. So this example is due to the authors, Conca, De Negri, and Gorla, but also, so this is from 2018, but also from inspired by work of Bernstein, Sturmfeld, and Zelvinsky in 1993. So if I have a big matrix variables, a generic matrix, and in order to keep it the same notation as before, it will have n rows and a columns. So an n by a matrix of variables. So here the ai's are all the same. They're all equal to a. And this is going to be graded by rows. So the entry xij as the degree as before, which was the ith basis vector of n to the n, which means this is the same as the row index. So this multi-degree remembers the position, the row in which the variable appears in the matrix. Okay, so then the ideal of maximal minors of this matrix is characterized Sturmfeld. And here, actually, there are two interesting cases. I mean, m here, maximal minors means it's the minimum of a and n. And in fact, the two cases are different because we're grading by rows, so we're breaking the symmetry. So both the cases where the maximum is attained by the number of rows or columns gives a characterized Sturmfeld ideal. And the fact that this, in some cases, give a universal Grobner basis was precisely the contribution of Bernstein, Sturmfeld, and Zelvinsky in 1993, which was one of the starting points of this theory. More determinantal ideals. So with same notation, same matrix, we also have 2 by 2 minors of generic matrix. They form a characterized Sturmfeld ideals. This is actually the characterized Sturmfeld paper. So this is a subject of 2010 paper by these two authors. So the idea of 2 minors is characterized Sturmfeld. Of course, they didn't phrase it like this. But we should emphasize that the 2 minors, in this case, define the diagonal in the product of projective spaces. So what do we have? We have delta is the small diagonal in the product of projective spaces. So as I said, this is the case where all the AIs are the same. So we have a product with n factors of some projective space, and the small diagonal is defined by by the 2x2 minors of the generic matrix. You can change these two examples. They don't really have to be generic variables. I mean, they don't have to be independent variables. They can be just multigraded. Any multigraded linear forms with this grading will also produce characterized Stumpfels ideals, because this class is closed and there's specializations, basically. But the intermediate minors will not be characterized Stumpfels ideals. I thought this was an interesting, I mean, something that is not clear from now, because they also have square-free initial ideals, but still they're not characterized Stumpfels ideals. There's many more examples. I will just mention a few more. Some are well known. So, for instance, one that is a partial generalization of this last example is the famous class of binomial edge ideals. So this was also proved by, again, the same authors. So here it's essentially similar to the previous case, but we only have two columns. So take a matrix of variables with 2 columns and n rows. Again, graded by rows, but we don't take all the minors. So we construct an ideal, a binomial ideal associated to some graph. Okay, so if G is a graph on n vertices, on the set of vertices 1 to n, corresponding to the rows, then we construct an ideal that is generated by the 2x2 minors that correspond to the edges of this graph. So here we pick, for instance, row I and row J, where IJ is an edge of this graph. Okay, so this is a well-studied class. Probably a number of papers on this subject is in the thousands, I would imagine. But this is a characterized Stumpfels ideal. So in fact, this, for instance, gives a sharp upper bound on the regularity by what I said earlier, and other interesting information. There's more. There's a class that generalizes directly the class of 2 minors. If we think of this as essentially a linear space in the product, then we can generalize it. So it's not literally a linear space, it's the closure of one. So we get closures of linear spaces. Again, same author, but this time some of the results were already proved in a paper by Ardila and Booker in 2016. So the objects in here are, you start from a linear space in the product of affine spaces. Okay, so you take the corresponding product of affine spaces. That's itself a big affine space. And you take a subvariety that is a linear space, so something generated by polynomials of degree 1. And its closure, in general, will not be generated by linear forms, right? So its closure will be whatever interesting subvariety of the product. The diagonal from before was an example of this. And the ideal that defines this subvariety is always characterized Stumpfels. There is more. I'll just mention one without going into details because I don't want to spend too much time on examples, but there's many, many more. So some come from computer vision. So these are called multi-view ideals. And I know there's ongoing work on this topic, even from the perspective of characterized Stumpfels ideals. So different sets of authors have studied different aspects of this class, which can be unified in this notion of CS ideals. Okay, so I'll stop here with a quick overview of the theory of characterized Stumpfels ideals that has been developed, say, in the last 6 years, more or less. And I want to go back to the definition of characterized Stumpfels ideals for a second. So here we go. So this is a definition of when an ideal is characterized Stumpfels, but if we pay close attention, it's the condition, especially 2, 3, and 4, they're not really conditions on the ideal I, but rather they're conditioned on the Hilbert function of I. Okay, so I doesn't appear in any of the four statements. This is really a statement about the Hilbert function of I, or even more precisely about the class of all ideals with the same Hilbert function. Okay, so this is most explicit in condition 3. So this is something about all ideals with a fixed Hilbert function. In fact, this definition is saying is that if we fix a Hilbert function, either all ideals are characterized Stumpfels or none of them is. So this means that maybe the best perspective for studying this class of ideals is to study all of them together, and is to look at the Hilbert schemes of characterized Stumpfels ideals. So let me talk about that for a second, and let me recall a definition / theorem from the seminal work of Heyman and Sturfels. In 2004, which gives the right perspective on this. So here we go. So we're given a function h, which we should think of as the Hilbert function of something, or just a numerical function from the semigroup of degrees to the integers. Then there is a projective scheme, K-scheme, that I'll denote with curly h, upper H, lower s. So curly h stands for Hilbert, and then we remember the important data, the function and the polynomial ring where we're working. So this is parameter space that parameterizes all the homogeneous ideal of the polynomial ring with the given Hilbert function. So such that the Hilbert function of that ideal or quotient is equal to the function we're fixing. And this object is called the multigraded Hilbert scheme. So actually the definition is much more general than this, but for today we'll stay in this n to the n graded setting. And okay, so this is what it is. This is the moduli space of ideals in a graded polynomial ring with a fixed Hilbert function. So here I'm giving a very informal definition as a set, but clearly this is more than a set. I mean, it says here that it is a scheme, so it does in fact a functorial property. I mean, it's defined as the object that represents the functor of flat families. And this gives the object a natural topology, a natural scheme structure. Sometimes it is a projective variety, sometimes it is in fact a scheme and with a non-reduced and interesting scheme structure. So we really have to call it Hilbert scheme. And this is, roughly speaking, the right place where one should study deformations and degenerations of ideals and varieties and schemes. Okay, but for today's we can think of it informally as a variety or scheme, more appropriately, that parameterizes all the ideals with a given Hilbert function. Okay, then in terms of this multigraded Hilbert scheme of Heyman and Sturfels, we could recast the entire discussion that we had earlier in the following definition. We can say that a multigraded Hilbert scheme is characterized Sturfels if all the ideals that it parameterizes are radical ideals. So if I is radical, for all of the ideals parameterized. Again, so that's the same condition as before. All the ideals with the same Hilbert function are radical. I should emphasize that this is, once again, especially from the perspective of Hilbert schemes, it is a very strong requirement. It's a very strong assumption. Usually what happens with these parameter spaces is that the general member, the general object that we are parameterizing, maybe it's nice. So it could be like a smooth curve in P3 or a reduced set of points. But then as we go to the boundary of this compact object, there are some degenerations that are pathological. Okay, so we could have an object that is a limit of very nice object, but itself is very pathological and particularly non-reduced, non-radical. So here instead we're saying that even on the boundary, even the most degenerate examples of ideals that live in this Hilbert scheme should still be decent enough that they're still radical. And another expression of how strong this is, so I'll repeat from before that we have learned that if multigraded Hilbert scheme is characterized Sturfels, then it has a unique Borel fixed point, a unique Borel fixed ideal J. Again, this is quite unusual for a Hilbert scheme. We know that Borel fixed ideals always exists, for example, by this generic initial ideal construction, but in general, there is many. So uniqueness is something that could be an indication that these parameter spaces are nice. They have good property. And in general, for any parameter spaces, for any moduli space, one asks the best questions, the best properties one can ask is, are they smooth? So in particular, they're reduced, so they're varieties and they're non-singular. If not, still irreducibility is perhaps these are the two nicest properties the moduli space can have. Okay, so maybe this is, I guess, a good time to take a break. So we'll see more about this after the break.
Perfect. Let's take a break. Does anybody has a question for Alessio? Okay, so we just take a break. So Alessio, please tell us if this Hilbert scheme is smooth or irreducible.
Yes. So the answer, of course, is sometimes yes, sometimes no. So just to recap, I think this is all we need to know from now on. So the multigraded Hilbert scheme parameterizes ideals in the multigraded polynomial ring with the same Hilbert function, and we're interested in those that are parameterizing exclusively radical ideals. We call them characterized Stumpf Hilbert schemes. So the most basic question, as we were saying, is smoothness and irreducibility. And this is, in fact, now a good time to go back to Cartwright and Sturmfels, meaning their paper that started all of this from 2010, because they really have this perspective of the Hilbert scheme. So they study the Hilbert scheme parameterizing all ideals with the same Hilbert function as the diagonal in a product of projective spaces. So this was either an ideal of two minors or of a generic matrix, or the ideal of of the diagonal, yes, in a product of P projective spaces of arbitrary dimensions. And yeah, so maybe let me write this better, because I need the parameter. So here X is an n by A matrix. And all of this connection between combinatorics and geometry was very clear and explicit in this first paper, because what they do is they study this, they can determine explicitly the unique Borel fixed point. They observe that this Borel fixed point is unique, and they start from there to try to understand the geometry of this parameter space. And they, among what the result that they proved very explicitly, they show that this Hilbert scheme is smooth and irreducible when we have two factors, if n is 2. And by that I mean, so A is irrelevant, so the important factor is having two factors, but otherwise it isn't. So equally explicit, you can cook up example of singular points and different components, so it will also be reducible if n is 3 in general. Still, the fact that you have a unique Borel fixed point, even if the answer is not always good, at least it gives a tool for answering the question in general. And so one could hope, and we did hope for that a complete classification was possible for smooth characterized Stumpfels Hilbert schemes in terms of the ambient dimension of the semigroup. So let me be more precise here. So what we're seeking here is a classification of the integers n. So remember, that's the number of components in the multigrading, such that every Hilbert scheme of characterized Stumpfels n to the n graded ideal is smooth and irreducible. So maybe every is confusing here. Yeah. So classification depending exclusively on the grading, on the dimension of the semigroup that you use for the grading. So this the Hilbert function. So this should be true for every Hilbert function and for every polynomial ring. So for every number of variables, let's say. And if we think about this question for a second, then we start. We understand, we see that the answer splits into three different answers. Namely, when n is 1, the situation is trivial in the sense that if n is 1, then we're in the context of standard graded ideals now. So what we're looking at is basically, so if I think, for instance, about the Borel fixed ideal J, here we only have one set of variables, a1 variables. So the Borel fixed ideal is supposed to be ungraded. Okay, Borel fixed. And radical, that's the key condition of Cartwright-Sturmfeld. But you don't really have many options here. So the only such ideals are the ideal generated by variables. So this has to be, this implies that J is generated by an initial subset of the variables. So for some B less than A, and then by semi-continuity, this has to be true as well for every ideal. Okay, so every ideal I in this Hilbert scheme is generated by some linear forms. So this is definitely not an interesting Hilbert scheme. But in particular, it is a smooth Hilbert scheme because this is really parameterizing subspaces of the variables. So this is a Grossmannian. So this is Grossmannian of b-dimensional subspaces into the space of variables. So in particular, it is smooth and irreducible. So that's the first of the three answers that we get. If n is at least 3, then we know what's seen already by Cartwright and Sturmfeld. There are examples where the Hilbert schemes can be reducible and singular. So that's by Cartwright and Sturmfeld in 2010. So we immediately get complete answers in all but one case. There's one case that remains, and that's really the only case that is interesting. When n is 2. So the cases of bi-graded Cartwright-Sturmfeld Hilbert schemes, where we saw that in the case of the diagonal, the Hilbert scheme was nice. So still the answer is unclear in this one remaining case. Okay, so that is our main contribution. Okay, so our main contribution is completing this classification. So this is, again, joint work with Ritwik Rankumar. From this year or maybe the next. So then good news, in the bi-graded case, all bi-graded Cartwright-Sturmfeld ideals, sorry, Hilbert schemes, are smooth and irreducible. Again, that means for every Hilbert function and for every number of variables. So in other words, for every polynomial ring. And just in case you're lost, or you lost the main definition. Once again, this means that every single ideal parameterized by the Hilbert scheme is radical. So I do want to talk about the proof, or some of the ideas of the proof. But before I do that, I want to observe that how this, in retrospect, this trichotomy, this three answers that we got, trivially yes when n is equal to 1, interesting and yes when n is 2, and false when n is at least 3, actually resembles two well-known stories where one has essentially the same question about Hilbert schemes, but they're different. So I want to talk about them for a second. So one is the classical Hilbert scheme, so the Grothendieck Hilbert scheme. So what that means is this is a different moduli space, so usually denoted by Hilb. Then there's a polynomial, PZ, and a projective space. So this is the moduli space for closed subschemes of projective space with the given Hilbert polynomial. So this is the one that came first, in fact. So in terms of ideals, we're parameterizing saturated ideals, not just homogeneous ideals. And instead of fixing the Hilbert functions, we're fixing the Hilbert polynomial. So that's the original Hilbert scheme, or classical Hilbert scheme. And if we want to ask about a classification of smooth and irreducible Hilbert schemes that is purely in terms of the ambient space dimension this time, then we get exactly the same three answers. So when n is 1, the answer is more or less trivial, because we're talking about Hilbert scheme of P1, so subschemes of the projective line. Necessarily, the Hilbert polynomial has to be an integer, let's say d. So then here, this parameter space, it's not hard to show that it is in fact isomorphic to projective space, dimension d. So it is smooth and irreducible for every d. And when n is at 3 or above, then, so when ambient space dimension is 3 or higher, then this is in general singular and irreducible, reducible. So singular is very easy to get. It's really easy to get example of singular points. Reducibility was one of the early results by Rubino in this field in his 1972 paper. And the interesting case, the only interesting case here as well, is the case when n is 2. So this is in fact a classical theorem. This is a theorem of Fogarty from 62 that says that the Hilbert scheme of a P2, or without really much modification of any smooth surface, is itself a smooth and irreducible variety for every Hilbert polynomial, always. And this is a very famous theorem, one that has sparked a huge research area about Hilbert scheme of smooth surfaces that still is very, very active. And so that's one story where for a different object, we had the same question and the same answers. And then there's another one that is multi-graded Hilbert schemes, but just arbitrary multi-graded Hilbert schemes, so not necessarily Cartwright-Sturmfeld. So it's a slight change of perspective from our earlier discussion. So this is, it's the same object, so we're parameterizing ideal in a polynomial ring. This time I'll denote we'll call n the number of variables with a fixed Hilbert function. But an important difference is that here we are allowing the grading to happen, any sorts of grading, okay? So any semigroup, commutative, or decent enough in some sense. But for instance, we could have negative gradings, meaning some variables have positive degrees, some have negative degrees, some variables can have degree 0. The degree of a variable could be a torsion element in the group of degrees and so on. So in this context, where now we shift the attention to the dimension of the polynomial ring and not the dimension of the degree semigroup, then we could ask for the third time for a classification of the integers n for which the multi-graded Hilbert scheme is always smooth and irreducible. And answer is for the third time the same. So when n is 1, this is trivially the case, trivially because we are looking at homogeneous ideals in one variable, in a polynomial ring of one variable. So depending on how the degree is set up, this could be, the Hilbert scheme could be either a point, the empty set, or in the most interesting case, a Hilbert scheme of points in A1, which is itself AD, a fine space. So in any case, it's always smooth and irreducible. So this is not so interesting. When n is at least 3, the previous example isn't particular valid here as well. So this is singular and reducible in general. Maybe I should have said that the multi-graded Hilbert scheme is a generalization of the classical Hilbert scheme. But when n is 2, that's essentially the only interesting case, and that's a theorem of McLagan and Smith, who answered a conjecture of Heyman and Sturmfeld that says that this the multi-graded Hilbert scheme of a polynomial ring in 2 variables is always smooth and irreducible. Although here, so this is a theorem of McLagan and Smith, but there are also important precursors in some special cases. So I should give credits to Branson, Yarubino, and Levine for some special cases of this theorem that preceded the proof of McLagan and Smith. So the analogy is very, very strong, although I must say that I don't understand how deep the analogy goes, because the Cartwright-Sturmfeld Hilbert schemes are neither a special case nor a generalization of any of these 2 classes. So the fact that we got exactly the same answer, the same classification, is in some sense surprising. So that's, yeah, because the objects that are parameterized by these Hilbert schemes, in the case when n is 1 or 2, are essentially always zero-dimensional objects, essentially always sets of points in a fine space or projective space. Whereas in characterized Sturmfield's ideals, the objects are very positive dimensional, as we will see in a second. So there are different types of parameter spaces, although, yeah, the answer is surprisingly the same. All right, so I will pause to see if anybody has questions, and then I will say a few words about our results, and go back to our results.
Is there any hope to classify the smooth ones for, I don't know, n equals 3 or?
I'm a bit pessimistic in that sense. So I should say that so for these two stories that are better known, here the answer is yes. So here there is in fact a complete classification due to Skillness and Smith. There is a relatively recent result. So not just in terms of n, but also in terms of Hilbert polynomials. So here there's a complete classification of all the smooth classical Hilbert schemes. In this class of multigraded Hilbert schemes, I think this class is too large. There's just too many possible directions in which one can find a whole variety of Hilbert schemes. Just to say the Grothendieck one are just a very special case of this. So here it seems hard that one could, even when n is 3, one could classify in terms of all possible Hilbert functions, all the smooth ones.
I was thinking about your result with 3.
Yeah, for the characterized Sturmfields, I don't know. I know that there are some other families of smooth ones. So for instance, arising from computer vision, those multi-view ideals, some people are studying this smoothness of characterized Hilbert schemes in those contexts. So maybe it's a reasonable question. I wouldn't know. But thanks. Okay, so maybe I can tell you a little bit about the proof of our result. So our result is all about the bi-graded polynomial ring. So the number of components of the multigrading is 2, right? So our polynomial ring has 2 sets of variables, which we will naturally call x and y's. A1 of x's and A2 y's. So this is bi-graded. And xi have degree 1, 0. And then yj have degree 0, 1. Okay, so as I have indicated for the entire talk, the special feature here is the unique Borel fixed point. So remember that this is a unique, that the Hilbert scheme. So if we take a characterized Sturmfield's Hilbert scheme parameterizing multigraded ideals in this polynomial ring, then it will have a unique Borel fixed ideal that I will call J, as I've done previously. And this is a special monomial ideal. So in general, this is a combinatorial description. Here I can be fairly explicit with this combinatorial description. So basically, this can be encoded by a graph, a bipartite graph on the two sets of variables. So on the partition with corresponding to the x's and the y's. And the J is simply the edge ideal of this graph. Okay, so it's generated by the monomial xi yj, where ij is an edge in this graph G. Not all the bipartite graphs are good. I mean, you can classify in exactly which bipartite graphs will give rise to a Borel fixed ideal. That's not hard. The crucial fact about the bi-graded as opposed to n-graded characterized Dürfels is this information on the regularity. So the n is a bound on the regularity. So basically, if I take any ideal now, not the Borel fixed one, but an arbitrary point on this Hilbert scheme, then the regularity will be 2. Okay, bounded by 2, but of course, up to removing trivial case, it will be exactly equal to 2. And this is okay. This is a much bigger, more complicated class than that of ideals with regularity 1, but still is a class of ideals that has a lot of structure. So that's the main, the crucial point in this theorem. The fact this is a classical theorem of Eisenbud, Green, Jülich, and Popescu. So this is the zero locus. So not in the product, but it's just in one projective space. The zero locus of this ideal is what's called a small scheme. So there's an geometric interpretation of this condition of having regularity 2 that is due to, as I said, David Eisenbud, Green, Jülich, Popescu from 2006. That basically amounts to that is essentially the generalization to schemes of the notion of varieties of minimal degrees. And in this case, it really amounts, so since our points are also reduced, so this is amounts to being a configuration of varieties of minimal degrees that are linearly joined. So something that so linearly joined varieties of minimal degrees. Okay, so linearly joined is a particular condition that expresses some restrictions on to how these varieties of minimal degrees are connected to one another. But this is saying, of course, that the varieties of minimal degrees are the building blocks of these ideals I. So in other words, the building blocks of the non-monomial deformations of our unique Borel fixed points. So so the whole the heart of the proof, I mean, all of the work is in the next step, which is amounts to describing the deformations, so really all a posteriori deformations of J, of the Borel fixed ideals, in terms of the graphs, in terms of the combinatorial data. So somehow the combinatorial data of the Borel fixed point has to match up with the combinatorial data of how this building blocks, these varieties of minimal degrees are can be part of a possible configuration, let's say. So that's the main work in this proof. I'm not really saying anything about it, but once you do that, then you're done, because then you essentially construct a family of ideals that tells you that that gives a lower bound for the dimension of the Hilbert scheme near near the Borel fixed point. And you can also compute the tangent space at that point using the combinatorial data of the graph and show this inequality. Okay. So this means that in fact you're forced to have equality. So this means that you have a neighborhood of your Borel fixed point in the Hilbert scheme, an open neighborhood, and that this is the same dimension as the tangent space. So that's the same as saying that J is a smooth point in the Hilbert scheme, but by the standard upper semi-continuity argument, the fact that J was the unique Borel fixed point in some sense means that that this is the most degenerate point on the Hilbert scheme. So if that is smooth, then everybody else is smooth. So this is smooth everywhere. And also irreducible. I mean, irreducibility is just a remark once you have smoothness, since you also have connectedness. Yeah, so this was, I mean, just a conceptual sketch of the proof that with all the main ingredients, but without showing any of the work. Although I also have an example that I want to show you, so maybe that will give a little bit more details. What is it? Yes. So with this, I will basically go through the proof again. Unfortunately, in this situation, in order to get a meaningful, non-trivial example, you really need a lot of vertices and a lot of edges. So this is in some sense a small example, but it's already very crowded. So let's see, what do we have here? We have a bigraded polynomial ring that has two sets of variables, x's and y's, 7 each. And the Cartwright-Sturmfeld Hilbert schemes are in one-to-one correspondence with radical Borel fixed ideals. So here is an example of a radical Borel fixed ideal J. It is the edge ideal of a graph, a bipartite graph, where so we only allow edges between x's and y's. So here we have many, many edges, regardless of thickness and color. These are all edges of the graph. But I highlighted some of them because these are the only ones you need to remember. Okay, so if you think about the, if you think about the partial order of N2, the usual partial order, so you can only you only need to remember the maximal edges. Okay, so 1, 2 is not a maximal edges because it's dominated by 1, 6, for example. So in this sense, then this graph has 5 maximal edges, and these are the ones that I highlighted here: 1, 6, 4, 4, and so on. Then it will turn out that it makes sense to, in some sense, split this maximal edges. That first of all, that the maximal edges encoded all the important data on these deformations of J, and more precisely in the following way. So that would split them in 3 groups. And this corresponds to the fact that a general element in this Hilbert scheme will be a Cartwright-Sturmfeld ideal that has 3 minimal primes, has 3 components. And as I said, geometrically, the building blocks here are varieties of minimal degrees. So here, in some sense, these 3 red edges correspond to a Segre variety, to a P1 over P1 times P2. In fact, one has to take a cone over the Segre variety with a 4-dimensional center. And the green edge will correspond to just a linear space. So we have a 6-dimensional linear space as one of the 3 components. And this purple edge here will correspond to a smooth quadric in an 8-dimensional linear space. So in this case, our combinatorial argument, I mean, not our analysis of the deformations of the Borel fixed point tell that all the deformations are of this form. I have 3 components: a smooth quadratic surface, a linear space, and a cone over a Segre variety. In general, there's a process to produce all of them, but it becomes a little bit more complicated too. Yeah. Okay, yes, so this is more or less all that I wanted to say. Maybe I'll just end with some questions that are motivated. I think there's still a lot to say about this Cartwright-Sturmfeld-Hilbert schemes, and especially comparing with all that we know about other classes of Hilbert schemes. The question of singularities is perhaps the most important, the most obvious one. We know about Murphy's law in Hilbert schemes, how essentially every type of singularity can occur on some Hilbert scheme. But we've also seen that this Cartwright-Sturmfeld ideals and Hilbert schemes are very special and very rigid. So the general question that I would like to ask is, what kind of singularities can occur on Cartwright-Sturmfeld's Hilbert schemes? Do we have all of them? So is there a Murphy's law for Cartwright-Sturmfeld's Hilbert schemes? That's completely unclear at the moment. And if not, then the main question is about their natural scheme structure, whether they're always reduced. In general, whether a Hilbert scheme is reduced or not is a very delicate question. And for instance, for the Hilbert scheme of points, the answer was given just very recently by Joachim Jelisheyev. So, but this brought new tools and new techniques that maybe can be applied in this context as well. And then there are a question that is more inspired about the more commutative algebra part of the story. That is the following question: is it true that if an ideal is not only Cartwright-Sturmfeld but also prime, then is it smooth? Because from the point of view of Cartwright-Sturmfeld's ideals, prime ideals are very special, and I think they're always Macaulay. And in general, yes, that's. I've also tested this question in many examples, and I haven't found a counterexample. So yes, and then there's other questions, like in all of the examples that are studied in the combinatorial literature, like for binomial edge ideals. Can we use the combinatorics to say more about these Hilbert schemes? But yeah, I don't want to bore you with more and more questions, so maybe I'll just stop here.
Okay, I would like to thank a lot Alessio. Please.
Thank you.
And Alessio, are there any questions for Alessio here?
If you take tripartite ideals, three sets of variables, I guess you also can get these things. Could there be a classification there too?
Yeah, no, this is kind of related to Claudia's question too. Yes, I don't know what to say. So of course, the first answer is that I haven't tried very hard up in the tri-graded. I haven't tried at all, and of course, there's considerably more variety there, because here this two regular situation made the entire situation fairly rigid. For three regular, I presume it's going to get a lot more complicated. Maybe one could find a classification if most of them turn out to be singular, and maybe that's a possibility. But I really have no idea at the moment. So something to be investigated. Yeah.
But there's at least a combinatorial question, which is how to describe the dimension of the tangent space at this.
Yes, so this is...
So for graphs, is there a good way to say the answer? I mean, what's the dimension of these Hilbert schemes?
Unfortunately, there isn't an easy answer. I mean, not a quick one that I can give you. The best I can tell you is that we give it like a recursive construction of these Hilbert schemes by defining a way that even here is not so obvious, like how to split the set of maximal edges into different parts that in the end will correspond to different irreducible components of the general member. And then once you do that, you can construct your Hilbert scheme recursively as a relative Hilbert scheme over a smaller one, basically. But it's yeah, the formula for the dimension is not nice. That's what I can say. That there's not a... Yeah, we decided to do this recursively. That was the only tractable way of doing it, but I don't think you can get a nice formula for the dimension.
A nice story. Very nice.
Thanks.
Yeah, very nice story. If there are no other questions, I would like to thank Alessio again for the fantastic talk.
Thank you.
Okay. Thank you, Alessio. Thank you very much.
Thank you.